set of stairs on the right as you walk into the old part of the building. If you go to the basement, it's a very safe place. We're going to be passing around the attendance sheet. So we'll be passing around the attendance sheet, and we'd like to ask everybody to sign it. This is how we document the expenses for the reimbursement for the pizza and soft drinks. And if you did not receive a direct email announcement about this seminar but would like to in the future, please legibly write your email address on there and we'll add you to the list. I'd like to welcome those of you who are participating via the telephone and internet, and remind you that if you would like to receive CEUs for your participation, please send LB an email with the information as described in the email announcement for this seminar. Joining us today on the phone are representatives from the URS Corporation, Transportation Technology Center, HDR, Amtrak, CSX, Wisconsin DOT, Amstead, U.S. Army Construction Engineering Research Lab, Zroka Engineering, Metra, Railstar Engineering, Transport Environmental Systems, Talon Research, Hansen Professional Services, Rail Sciences, Michigan Tech, Metro Council Southwest, CH2M Hill, University of British Columbia at Okanagan, Jacobs Engineering, and representative from Parsons Engineering. We want to welcome all of you who are participating in this seminar today. We appreciate your participation. I'll also ask the speaker if you could, depending on how people are tuning in, if you could periodically mention the slide you're on just so they can follow along. And if people here ask a question, if you could repeat it for the benefit of the audience. So at this time, I'd like to introduce Brennan Corin for a moment, who's AREMA Student Chapter President.
Good afternoon, everyone. Today, the AREMA Student Chapter is going to be hosting a happy hour in honor of today's seminar speaker. It's going to be at the Lime Kick Brewery on Neal Street. We're going to start at about 5:30, so we hope to see you there.
Thank you, Brennan. The William W. Hay Railroad Seminar Series is sponsored by Norfolk Southern Corporation here at the University of Illinois at Urbana-Champaign. And on behalf of all of us here at the university, as well as all of the people participating via the internet, we thank Norfolk Southern for their ongoing support. It's greatly appreciated by all of us. So a little bit about our presentation and our speaker. Railroads are paying increased attention to structural health monitoring to improve bridge safety and performance. Various new technologies have been developed over the past decade. In particular, wireless smart sensor hardware and software are becoming more effective and affordable for infrastructure owners to use to assess their bridge condition. And there are particular benefits to use of these technologies on railroad bridges, as our speaker today will discuss. He's going to describe some research being conducted here at the University of Illinois on development of a reference-free estimation method for bridge displacements under train loading. Professor LaFave completed his BS and his MS in civil engineering here at the University of Illinois, and his PhD in civil engineering with a focus on structural engineering at the University of Michigan. Before returning to his native Illinois, Professor LaFave was a faculty member at the University of Massachusetts for 2 years. He's also a licensed professional engineer with professional engineering experience at Wisjani Elsner and Sargent and Lundy. Professor LaFave's primary research interest is in experimental behavior and analytical modeling of structural connections and joints in a variety of contexts, including railroad bridges. In 2010, his peers in the U of I Structures Group asked him to serve as the chair of their group. On a personal note, Jim and I both joined the U of I at about the same time, so he and I have kind of grown up together here, and so it's particularly gratifying for me to see him doing such nice cutting-edge research on railroad bridges. Please join me in welcoming our speaker today. Professor James LaFave will present the William Hay Engineering Seminar today, entitled Structural Engineering Research for Railroad Bridge Performance Assessment.
Hey, thank you.
Okay, thank you very much, Chris, for that nice introduction. As he indicated, the title of my presentation is Structural Engineering Research for Railroad Bridge Performance Assessment. Before I go any further, I want to give special credit to a graduate student, Fernando Moreu, who has been the student who's been doing a lot of the work I'll be talking about today and who was of great assistance in preparing many of the slides and other information. And also to all the facilities and railroads listed here as well, who have in one way or another provided support, in particular the Smart Structures Technology Lab in terms of some of the field work I'll describe briefly toward the end of the presentation. since I'm kind of wearing the hat of both the seminar speaker today and also kind of a representative of structural engineering and the structures group here at the University of Illinois, I wanted to start my presentation by getting off on a little bit of a tangent for just a handful of slides to kind of maybe put what I'm talking about today into the biggest and broadest historical picture. In the same way as the railroad engineering program here at the University of Illinois has a very, very long tradition, I think the participation of structural engineering researchers within that program also has a long and storied history. The likes of Talbot, Wilson, Newmark, Hay, and then more recently Fouch and Gamble shown here, who did research related to riveted joints, steel beam fatigue, lateral longitudinal loading both on bridge structures, and more recently pre-stressed concrete, have all been examples of the structural engineering group interfacing with the topic of railroad bridge research over the last 100 years. In the same vein, even today, we have a very strong group of 13 or 14 faculty in the structural engineering and mechanics program here at the University of Illinois in civil and environmental engineering, and probably half or more of these individuals have been directly involved in railroad research in one way or another. And I would say that more broadly, the coursework and the research that they conduct may or may not directly always affect railroads and railroad bridges, but I think the things that students learn in the course have many applications to that field. And so to very briefly keep this slight tangent going, I just wanted to give a quick listing of some of the broad research interests of our structural engineering and mechanics faculty here in the present day of 2012 that ranges from the very practical, maybe in the upper left, a bunch of things you've all heard of, to the research frontier more down in the lower right, where you hear about things like risk and reliability, structural health monitoring, fancy new materials that are emerging, et cetera, et cetera. So to complete this sort of introduction in the broadest sense related to structural engineering here at Illinois and how it has connected to the railroad engineering program and railroad-related research, I'm just listing here a handful of recent examples of UIUC CE structures faculty having involvement in railroad-related research. A few years ago, Professor Dan Kuchma, who's here in the audience today, did some testing for strength evaluation of aging concrete railroad deck beams. Right now, Professor Larry Fonestock is involved in a project on improved bolted connections for special track work with a focus on crossing diamonds. Professor Bill Spencer is here as well, has great expertise in wireless structural health monitoring, with a particular example being the so-called government bridge. Professor Bassam Andrawas, along with Dan Kuchma, is working with the big team on improved concrete railroad tie design and performance. And then I'm going to talk a little bit today about one narrow slice of bridge performance assessment using simplified field monitoring. That is in addition, of course, to some construction materials and other faculty who are working, John Popovitz, David Lang as well, on topics very closely related to railroad bridges and very closely aligning themselves with structural engineering. So in terms of the slightly more narrow focus topic for today, bridge performance assessment using simplified field monitoring, the general background is that there's an ongoing need for repair and replacement of railroad bridges, and there's an issue that there's limited access to them during actual traffic, and so it may be challenging to measure year-to-year degradation. And so perhaps bridge management could be improved by measuring changes in bridge performance by using some sort of sensors, wired or maybe even ultimately wireless, to collect data that can become part of the bridge record that could assist in some way in bridge repair prioritization under the general umbrella idea of performance assessment for maintenance. And so what I want to talk about today then in that vein is, first of all, for a few minutes, talk about some important preliminary work that was done to just get a better handle on research needs within the railroad industry related to bridges and structures in general. And then after that, briefly talk about the monitoring approach. One field excursion where on a timber trestle some displacement measurements were made with the help of folks from CN, and also some acceleration measurements were made, and in tandem, as I indicated earlier, some folks from the Smart Structures Technology Lab here also were making wireless measurements, and I'll try and describe in general what that research has shown to date in that field effort and where it might go from there. So in terms of the preliminary work, there's two things I want to talk about. One is a survey-based study that was conducted over the last couple years, and then the second is an ongoing effort toward what I call railroad bridge classification. The survey-based study was basically something that was conducted over roughly the last couple of years to try to determine for railroad structural engineering what are the current research needs. The effort was focused here at the University of Illinois. I mentioned Fernando earlier. He and I spearheaded it, with him doing most of the legwork, and the goal was to determine current research interests and needs related specifically to railroad bridges and then more broadly to structural engineering in general. The motivation for doing this was that about 25 years ago there actually had been a national workshop on a related topic held right here on campus that resulted in sort of a white paper type document that was able to identify the most important research topics of that day regarding railroad bridges and structural engineering. And many folks have noted that the amount of sort of related research activity in the era leading up to then was sort of trailing off with respect to railroad bridges, and it picked up a bit in the era after that. So the idea was that as a minimum objective, if one could conduct some version of a survey that might be a surrogate for an actual workshop, it could help prioritize what are the current railroad bridge structural engineering research topics as given by members of the community across North America, and that since it had been quite some time since the previous such survey or workshop, in that case, this could be very beneficial to the profession. So in terms of the survey methodology, just to give you a very brief idea of what was done, the project started with Fernando and me talking to various people in the industry to come up with kind of ideas about what would be appropriate questions to ask, open-ended, and also topics to survey about. These were emailed to various interviewees with questions and topics, and followed up with phone interviews. Along the way, some additional topics were added to the initial list, and the interviews were continued, and follow-ups were also completed with folks that maybe had been talked to early in the process before the full list of topics was complete. And then finally, there were meetings in person, if possible, to discuss matters further. On the side, some literature reviews, meetings with other experts, etc., were also conducted. In terms of the population, this was not a large survey in terms of the total number of people surveyed. It was targeted at something on the order of 16 primary participants, but they represented a wide range of experience in the railroad industry, representation of different organizations that had to do with the railroad industry, fields of expertise related to the railroad industry, and other professional committee and other involvements. What came out of this survey then were 22 main research topics, and those included among them topics that were originally proposed by us when we started the survey. Also, some new topics were collected along the way, and a handful more came out of the related literature review. All of this can be found now in a Newmark Structural Engineering Laboratory Report Series document dated just last month that recently came out that goes into great detail of summarizing all the aspects of this survey. Even though there were 22 main topics collected, it was found that about a half dozen of them seemed to be the current top research topics that came out of the overall survey. Those were also summarized in a bit more cursory form in a short RTNS magazine article that was published roughly 1 year ago. And so out of the current survey from the last couple of years, some means to make accurate deflection measurements on in-service railroad bridges, along with concerns about high-speed train effects on bridges and structures, long-span bridges that might be needed to replace existing aging bridges over major river crossings, issues about approaches, both from the bridge and the non-bridge perspective. Longitudinal force issues were important, as were concerns about new design loads. So with the survey sort of in place and in mind, then the thinking going forward is that one parameter that might be of interest to folks in the railroad field with respect to assessing or monitoring bridge structures could be lateral deflection. So that focused the ongoing research a little bit further. Along the way, one other activity that I want to just briefly describe was also conducted, and that was an effort to try to create a bridge classification of typical railroad bridges in North America, to better understand what the full collection of bridges are, and to also perhaps get some traction toward better understanding what part of bridges should be monitored depending on which type of bridges you're interested in. This is pretty much still a work in progress, but it's being done in conjunction with railroad bridge inventory. And the idea is that among the main classes of railroad bridges between timber, concrete, and steel, there could be as many as 11 different frequently occurring categories based on the superstructure and other aspects. And there may be various performance challenges or concerns in the industry about different of these bridges that are specific based on classification type. And many of the structural health monitoring applications so far are directed to certain subcategories of these bridges, or in some cases, things similar to that are directed toward accident prevention and not so much toward maintenance or routine inspection operations. Out of this then came kind of a set of classifications that aren't completely complete, but you can see an example of them here. This was conducted also in part in conjunction with the REMA Committee 10. The graduate student involved in this work, Fernando Murillo, is a member of that committee, and so a lot of this classification information was run by members of that committee. Examples of what we're doing for each of the 11 categories is to just basically define what is this class of bridge in terms of a general description, what are some of the most basic structural engineering issues that occur for that type of bridge, in particular for its superstructure and its substructure, in hopes that once we complete this effort and make it available, it could be helpful to those in the field that are interested in bridge assessment, monitoring, and the like. And so we're doing this, as I indicated, for a whole group of different typical bridge classes. So then the next step that I want to talk about today in bridge performance assessment using some simplified field monitoring is to then say that, okay, if based on a survey-based study, there's interest in measuring deformations or displacements, and if that is something that's important for railroad bridges, then perhaps we can explore the applicability of available measurement techniques or emerging ones to estimate these displacements. And so displacements at specific locations could be a performance parameter that could be of interest for certain classes of bridges in certain situations. And so we proposed using accelerometers for reference-free displacement estimation of railroad bridge deflections under railroad traffic. And so in terms of displacement as a simple bridge performance parameter, the idea is that as a train is passing over a bridge structure, it's going to create vertical and perhaps lateral displacements, and measuring them may be a bit of a challenge. And if some traction could be gotten with respect to measuring peak displacements or time histories under trains for both short and long-term assessment, that could come in handy. And so current methods are not particularly capable of monitoring displacements without having a fixed reference point, which is always a challenge. So with that in mind, as I already indicated earlier, there was sort of a parallel motivation in this effort that maybe down the road it would lend itself well to measuring reference-free displacements using emerging sensor technology from the group of faculty led by Professor Bill Spencer here in the Smart Structures Technology Lab as well. And other recent studies had proposed displacement estimation from acceleration, so that's the direction we were headed. And so if we could use sensors to obtain some sort of reference-free displacement measurements of railroad bridges under actual live loads, then by doing some field experiments, maybe we could demonstrate the concept, and then perhaps down the road it could be implemented with even fancier and emerging sensor technology. Whereas if we wanted to have a robust field experiment, it would be best if we could actually have real LVDT displacement measurements to compare against, to compare our actual train displacements with those that we could estimate. And so what I want to then describe in sort of the last part of the presentation is just a little bit about some field experiments that were conducted to explore the validity of displacement as a measure of bridge performance, especially from acceleration measurements. And what came up was there were some perishable opportunities that occurred where, in conjunction with Class 1 railroads, some nearby bridges for potential testbed sensing implementation were determined in conjunction with both CN and BNSF. I'll primarily talk about just one CN timber trestle bridge here today. And these were targeted to try and integrate some of the most pressing problems with the railroad with the work that we were doing here in the department, that we were thinking of doing. So there were 3 different field monitoring campaigns that have been conducted so far. One on a CN timber trestle down near Edgewood, Illinois, and then 2 more that were conducted near Burlington, Iowa, where an old BNSF steel pin truss and then a new BNSF bridge there both happened to temporarily have pier access to make reference displacements to compare to reference 3 displacement estimations. In each of these cases, the graduate student I described, Fernando Moreo, along with assistance from Professor Spencer's group and graduate students and postdocs, paid visits to the site. In the case of the CN timber trestle, there was also a lot of help from CN in terms of establishing through Sandra Scola and then also Hote Lee a reference scaffold so that we could make actual displacement measurements. They also gave us access to their wired LVDT and accelerometer data that I'm going to mainly be presenting here today, and assisted in many other ways. And so we're very thankful to that help from the railroad. In terms of the experimental setup at this first case then, it was primarily at one south trestle, as you can see here, immediately adjacent to the main span, which was a steel span, obviously. And the instrumentation included 2 LVDTs from CN measuring vertical and horizontal displacements with respect to a reference scaffold that had been included. We also had from CN some wired biaxial accelerometer information, and as I indicated, there were also some additional wireless sensors brought to the site by others at the U of I to compare and contrast readings later on. Measurements were made on 10 work trains and 4 regular trains. This is just a video showing not one of the work trains, but just one of the regular trains passing over, and just what the direct measurements of acceleration and displacement were for this case as it passed over the first timber trestle in question. And this is the lateral displacement and acceleration data obtained via the CN group that was assisting us. In terms of the work trains, we ended up having, as I indicated, 10 of them. They were run at speeds of 5 through 25 miles an hour in each of the 2 primary directions, over and back. This bridge just had 1 track on it, so there was no effect of 1 track versus the other. The measured displacements that we have on the left are for vertical displacement from the actual LVDTs at the site provided by CN, and then on the right are the transverse displacements that were collected as well. You can see that the vertical displacements indicate very regular response with axle loads passing over the actual trestle that was being instrumented. These displacements here are in millimeters. Pretty much everything else is in inches, so I apologize for that small difference. There's also been a normalization done here to get a common time scale across all of the different speeds of trains that were passing over this particular structure. And so it's referenced to the time scale that was actually in place for the fastest of the trains, the 25-mile-an-hour case. On the right, you can see that the transverse displacement information is much less regular, much more messy, but for this point in time, I just wanted to present in general what it looks like. A specific example then of these measured displacements versus time of the trestle, both vertically and also horizontally, is shown here for one particular work train passing over the trestle. You can see again the vertical displacement in the dashed blue line is very regular as the axles are passing over this trestle, whereas the transverse displacement is a little more complex. And even the transverse displacement has a modest pseudostatic trend in the negative direction, favoring one side versus the other in terms of the way it was displacing under load, in this case under a southbound work train. In terms of then the maximum displacements that were measured, again taken from the wired sensors that were put on in conjunction with CN, we can make some very simple observations to get started, even though the main effort here is ultimately to come up with some reference-free displacement measurements. We thought it best to, as an intermediate step, just understand what was coming from even the direct displacement measurements that we were able to make. And so the findings were that in general, the vertical displacements are fairly independent of train speed over this range of speeds. The horizontal displacements, on the other hand, increase with train speed. And then the train response when over the bridge is often said to be able to be controlled with slow orders, and this would indicate that that would appear to control the lateral but not the vertical performance of timber pile bends. Probably nothing too terribly surprising in that finding. As far as then the vertical and horizontal accelerations versus train speed, again, this is simply a plot of maximum values in the two directions. You saw what the actual signals look like a little bit earlier. The accelerations tend to increase from 5 to 15 miles per hour, and after that seem to not clearly increase as much. Maximum accelerations didn't seem to have the same trend as maximum displacements in general, and if transverse displacements increase with speed, perhaps based on what is seen between these two summary slides, some more information about transverse displacement could be useful to quantify bridge performance in some limited situations. And so, shifting gears a little bit, the next step was to try to basically see on a first cut what could be obtained from the wired acceleration information that we got from CN at the site in terms of how it might be able to predict any or all aspects of the measured displacements that were obtained there as well. And so what was found is we could estimate displacement simply by double integrating the measured acceleration and then comparing to the measured displacement for validation. And so how that ended up looking was something like this, where the estimated displacement has some features that look similar to the measured and other features that look a little bit less similar. In general, one issue is that the measured displacement seems to, even in the lateral direction, have this pseudostatic trend. It's not symmetric, whereas the estimated displacement does not have such a trend. It's essentially a zero mean result. Even so, the maximum values and a lot about the ranges we see are quite similar to the measured displacements that were actually obtained from the LVDTs at the site. In terms then of another example, the wireless accelerations that were obtained using the equipment from the Smart Structures Technology Lab were also used, and they were attached not only to the top of the timber trestle, but also to the scaffolding as well. And so in that context, one could just use the same procedures to try to estimate from the scaffolding accelerations whether scaffolding displacement was significant or not. And so it was determined, basically, to make a long story short, that while there were some scaffolding displacements, and while those could in fact be corrected for, the scaffolding correction did not really have a significant effect on the overall displacement estimation. We can also compare then the displacements that are measured to various lateral displacements, as I've already indicated, and do the CN group that I've already described, and then superimpose on that the ones from the wireless sensors that were brought to the site here as well. The measured lateral displacement, as I said, is non-symmetric. The maximum values and ranges of lateral movement are fairly well estimated, but the wireless sensors do appear that they can estimate displacements from a standpoint of both their maximum value and perhaps also their range. The measured pseudostatic trend could also, as an attempt, be removed by detrending measured displacements to see how, if it was a zero mean, it would match up to these calculated displacements. And so that's done here. And the results indicate that the estimated displacements versus the detrended measured displacements match up quite well. Now, in reality, what was really needed is not a way to detrend the actual displacements to get to the estimated calculated ones, but rather a way to trend, if you will, the estimated calculated ones to get them to look like the actual full real measured displacement record. And so that's one of the future challenges, unless the only interest is in dynamic range, in which case what's being done might be sufficient in certain cases. So in terms then of looking at other aspects here, one can look at the total range of displacement estimation, the maximum peak-to-peak displacements here, and note that except for an anomaly that appears with the 20-mile-an-hour train, the displacement range estimates seem to improve with higher velocities, in percentage basis at least, and the pseudostatic component definitely appears to affect the accuracy of these lateral displacement range estimations. As a final step, because there were additional accelerometers only on Pier 2 and Pier 3, but no displacement measurements, this information, also from CN, was able to be used, and following the same procedures, could be used to estimate deformations of Piers 2 and 3. And incidentally, Piers 1, 2, and 3, Pier 1 is the one I've been talking about most of the time. Piers 2 and Pier 3 are a number of piers away from that, farther away from both the end support and the main middle long span. In terms of what was found then, the maximum displacement estimates for the different piers are shown here, simply using the CN wired accelerometer values and double integrating. And what is noted is that although, once again, this is fraught with all the limitations that I've already mentioned previously, basic information about estimated maximum displacements, even with those limitations, may be able to assist in identifying piers with larger displacements in a very quick and efficient fashion. Additional information about longitudinal displacements and using the same procedures could be determined as well. As far as everything I've talked about so far, it's been related to the work trains passing over this timber trestle structure, but measurements were also made in terms of actual LVDT displacements and actual accelerations for loaded trains. And so that information can be presented here next. What you see here then is some dynamic displacement estimates for a regular train. Obviously the signal is a lot longer and a lot more complex, but once again the estimation of displacements shown in the lower figure and ranges from accelerations is also possible with in-service trains. Now, if this was a vertical example, it would only be catching the dynamic part and not the pseudostatic part, and so similarly, in terms of the transverse behavior, that one aspect is obviously, for the time being, missing in this assessment as well. So in terms of a quick summary and some conclusions that I'd like to make for the talk here today that covers a little slice of some research that's ongoing in various different ways going forward is, first of all, the ability to make reference-free displacement measurements could be a promising contribution to an existing railroad bridge structural engineering research need, as seen from the survey of structural engineering and other professionals in the industry. For the timber trestle that was measured under work trains, lateral displacements increased with speed. Displacements have been estimated from accelerations using the wired sensors from CN in each case, with comparable results for the dynamic range of both work trains and in-service trains. Some other results from a 250-foot steel truss in Burlington, Iowa, both an old and a new one that I'm not presenting here today, also indicated some good promise for this general procedure using, again, wired and I believe also wireless accelerometers. And finally, other measures, perhaps strain measurements, perhaps tilt measurements, etc., might be able to, in some way, in conjunction with models of these structures, etc., be used to address this pseudostatic trend issue that I've noted here today. And there could be other emerging technologies in the future, things related to laser scanning, GPS, etc., that perhaps as they continue to mature may be complete alternatives to what's being described today. So finally, in terms of acknowledgments, I think I've already given a quick acknowledgement to many of the participants from the railroads and the other laboratories and facilities here today, but I just wanted to once again indicate that Graduate Research Assistant Fernando Moreo is the main driver for most of what I've talked about today. CN helped a lot with Hote Lee, Sandro et al. That helped us at the site. The Smart Structures Technology Lab, Professor Bill Spencer, his postdocs and graduate students helped with the wireless sensing portion that I didn't emphasize today, but was also part of this and in some of the processing of the information. And then finally, the AAR tech scanning program, and Dave Davis was sort of the initial impetus for doing this work in the first place. So with that, I'd like to wrap it up, and glad to try to answer any questions. I think our leading expert on this, Fernando, is off taking his Chinese class right now and might be back in a few minutes, and he can probably even answer some of the questions better than I can. So thank you for your attention. The other one. Very good guesser. Yes.
Several years ago in the class that we run on experimental methods, where we have one of those blue shake tables and we have the standard two-story frame, we tried an experiment where we put an accelerometer on the first and the second story, and then we also measured the displacement to try and do some of the things that obviously was a key point of the discussion today, but at a simpler level. And I was looking through the students' reports, and they had a few comments, and I'm wondering if your observations are consistent with what some of their comments were. One of them was in terms of the excitation of the shake table, they ran at a number of different harmonic frequencies, from 0.7 to 4.5 hertz, and then they ran a couple of earthquake records. And what their general conclusion was, they did a lot better at the lower frequencies in terms of getting good displacement data from the double integration of the acceleration than they did at the higher frequencies. And they also found some substantial benefit through trying different filtering methodologies. And so I'm wondering, with what you saw, were there certain sort of general things learned?
Yeah, I think that's one.
Better and where it doesn't work as well?
I think that's one of the biggest downsides probably of this field effort. It was like I said, a perishable opportunity that we took advantage of because it was available. And I think doing things more systematically like that, where you can vary more substantially the types of inputs in a laboratory setting, would be a good idea, because we're basically stuck with one particular bridge structure. It's work trains that are not much different from each other. And so I think that those are all very valid things, but they're things that weren't necessarily varying a lot in this particular study. And so I think going back to that sort of level as a next move to make sure that, for instance, if somebody's only interested in the dynamic part of it, and we're claiming that in fact we do a good job on that, and we really do a good job on that widely or just coincidentally in these cases. So I guess that's a full answer, but it seems like that's a great question that is not fully addressed here. Yeah.
I'm just curious about for the timber Dresdel experiments. Do you run the 10 trend sets only for once or for several times on that?
I think due to just logistics and the ability to get the work trains there for a reasonable period of time, it was basically once across and once back at each speed.
And also for the work trains, you have measured more than one times for the full loaded freight train run through the bridge? Since
Yes, I think there are, but that's just, again, was sort of more of a random event that once finishing with the work trains in the narrow window of time, there were that same day a number of regular fully loaded trains that went over the bridge, and data was collected for those cases, some of those cases as well. That wasn't the focus here, but that data is available.
Okay, so the data obtained here is only for, I mean, it's not the average value, it's only the one-time value. So
Right. For each speed, it's one-time value, and each, like I showed the vertical case, you can very clearly see when the rear axle group in front of the next adjacent cars are in the worst possible position, kind of like an idea of influence lines, the clear maximum vertical displacement, but there's no repetition to see how much variation there is in that. Now, vertically, I don't think there is a whole lot, but I think horizontally, this transverse behavior, which may be in part an artifact of what's happened previously in the structure that has some damage or is not, maybe not behaving symmetrically, may be more complicated. In other words, if two trains came from the same direction after some had gone the other direction, would there first be an effect of the first train coming in that direction, sort of resetting the structure in a new position, perhaps, and then the second one causing less movement. And that was not accounted for here because we just were going back and forth 10 times. That's it.
okay, thank you.
Yep.
Have you considered using some kind of multivariate statistical techniques to improve your estimates on this? Because it occurs to me you actually do have the capability. You collected data under some controlled conditions for set of food, and then, as you just said, there's a lot of trains going over. It seems to me that there's potential to kind of extract more information out of these data if you brought statistical techniques there. I guess.
Yeah, we have not done that yet, but I mean, that certainly makes sense. Are you thinking in particular for them when actual trains go over, or you're just saying in general?
I don't know.
Yeah.
I'm wondering. You do have a lot of data.
Yeah.
That's one of the advantages, and you have some, as you just pointed out, you have some highly controlled data.
Yeah.
And then you have a lot of data that are less controlled, and it seems to me that maybe you could. Well, a related question, and you and several others in the room can speak to this, is how much variability do you typically see in these kinds of measurements?
Well, I think.
Set of conditions?
Yeah, I mean, this is a condition that's very different than, we do a lot of laboratory testing here where there's obviously, variability in taking readings, but you can make it very, very small if it's just in the fully elastic range of some very well bounded structure with a very good sensor. There's some variability, but not a huge amount. In this condition, there's all sorts of different reasons for variability, and a lot of it can be just because the response is complicated and it may be different from case to case, not just related to the sensors or related to anything else.
Yeah, I guess what I remember from conversations I've had over the years with our friends interested in fatigue and fracture is that even if the quality, even if you don't have the absolute highest quality precision in your measurements, if you have a lot of data, sometimes the statistical approach will actually provide you with the information you need for something like this.
Yeah, and I think that's maybe where we're at in terms of just figuring out what it all means right now, but that might be a good next step. Yeah.
What was the sampling rate of the different technologies, and were you able to detect any impact to it?
Off the top of my head, I do not. That's where Fernando was here. I think he would recall that. I can't remember the exact sampling rate, but I think, for instance, for the vertical, where it's easier to see what's going on, not really. I mean, it's more of just a static excursion. I think for the lateral, I think there was, when the train, especially when it's coming from the south to the north, and when it just left the long span and entered the trestle area, often the first excursion immediately thereafter in one direction or the other laterally would be bigger than all the rest. So I think there is something to that. Yep.
Do you transverse displacements for the northbound train? There's a variability between the correlation between speed and displacement
that's something. I mean, we've heard some things from the railroads about some dynamic effects that they've seen in other cases that had some special behavior in that general speed range. And so I think this is where having repeated measurements where we could clearly say that we're confident in every single number there would be very, very helpful. And so I think I doubt that a clear comment on that would be wise, because I think that that could be anomalous measurement for one train excursion or something else. Yeah.
And I realized that you didn't measure the longitudinal displacement, right? So why do you do that? I mean, is that you think it's difficult to do that, or you think it doesn't matter?
I think that the displacements that were measured in this particular sort of perishable opportunity to join up with CN in the field were driven a bit by their interest about what displacements to actually measure. And so they were vertical and they were transverse. I think that subject simply to getting, in this case where we had a reference, getting some sort of a measurement device between that and what we were measuring, I don't think it would have been any more difficult once there was a reference there to make that actual measurement. Some estimates were, I glossed over it here pretty quickly just to focus on a few things, but there were some estimates of from acceleration only, of the longitudinal displacements, and they were actually larger than the displacements I was mentioning transversely in the actual talk, so they weren't insignificant, that's for sure.
And which dimension do you think is the key factor to structural damage?
Well, I think our study is more directed toward just exploring what's an issue for the railroad and how might you get a little bit of traction toward solving it. And so I guess we're, for the time being, not taking ownership of answering that question, but rather saying if someone can indicate that here's what's of greatest interest, here might be a way to make that measurement. I know there's interest, even in, you saw it in the survey-based study that I talked about at the beginning about longitudinal force issues, and so there may be reasons why longitudinal items are of great interest, and maybe even the longitudinal displacements would be of great interest. Clearly, an individual trestle by itself is much more potentially flexible in that direction than it is in any other direction until it's sort of interconnected with the rest of the bridge structure, and so that may be actually an area of greater interest. I think it was just easier to make these lateral measurements, frankly. Yep.
You mentioned that the lateral deflection was higher. Have you looked at the effect of wind speed on these?
It was no, we haven't. I mean, the day itself was fairly calm, and so I think we think that was sort of bordering on a non-factor, but yeah, absolutely, that was not something that we were focused on at all. Yep.
How do you think about the performance of estimating the displacement through the acceleration at higher speed? Because the data seems to have only through the 25 miles per hour. And if we can accurately estimate the displacement at higher speed, so it can also be installed on passenger train bridges. So like if there's a 70 mile per hour train run through, you can also estimate very accurately. So how do you think about the
Yeah, I think related to that, I didn't even mention that in one of these cases, an attempt to put sensors even on the locomotive was done, and I don't even recall what the processing of that information was. Obviously, again, it was limited from 5 to 25 miles per hour in this particular case. But yeah, clearly that's sort of beyond the bounds of what we were trying right here, but clearly it would be an important consideration whether it's on the vehicle itself or whether it's just these bridges being subjected to those higher speeds. Yep, right.
First of all, really good presentation. This is exciting. Great discussion too. In an ideal world, if we had limited financial resources and we were pursuing a field site to answer the same questions that you're trying to answer here with respect to understanding accelerations and displacements under a variety of input loads, what would you do to best characterize the input loads? Because we're kind of, other than knowing that we have loaded trains, revenue trains, work trains, we don't have a lot of information on what's being imparted into the wheel rail interface and down through the bridge timbers into this
Well, I think this is more taking the approach of one thing I didn't really emphasize is that perhaps stuff like this, even as maybe imperfect as it is, can be used more through calendar time to assess how similar or different the response is now to a year from now to later on, in which case perhaps having similar inputs each time is sufficient to start to make that assessment. Whereas if you're really trying to fully understand the response of the structure and the input, I mean, you know, better models of the structure are needed, information about the stuff you're talking about interface and rail issues are needed, et cetera, et cetera. But I guess that wasn't the main direction that this was pointed in, so I don't think I really thought about that much at all, frankly.
I see that Fernando joined us, so maybe a question about the sampling rate.
Oh yeah, there was some question earlier about for the sampling rate in the CN case, and I wasn't.
So for the wire data
Yeah.
with the CN implementation, we want all 100 samples per second, both displacement and acceleration. Is that all what they were asking?
I think so, yeah.
In the wire data collection, I said they are both the same sampling rate. The wireless, they were 880 for acceleration. So for this experiment, they were both of them were good.
Okay, and I guess there's a question maybe related to that that asks about the frequency of accelerometer data collection required for a good estimation based on double integration. And so again, the rate that you had for the speeds we had and everything was adequate, right? I mean,
Yeah, and also when we were at Women's here, some we talked about the presentation that was part of the presentation today. The general reaction to that was like, well, if you are measuring displacements at the end and based on the timber and the bridge and the height, 100, which was the lowest that we had, it was people went away without a concern. They were anticipating something much smaller. That sampling rate is good for working.
If there are any other questions, I want to thank you very much.
oh. Some just popped up here.
We have one more question online.
The last question is about horizontal displacement. Did a geometry car go over the bridge to measure any discrepancies in rail cross level? And I don't think so.
Get that done.
I mean, from
Have you obtained geometry car data on
just
of that stretch of track to see, to check cross level or gauge? Yeah, exactly.
you're saying it's readily obtainable? Is that
You can get it.
okay? Well, that's something.
That's a good point.
Okay. All right. That was the last online question. Sorry, Chris.